Hi and welcome to Module 5 of Geometric Computer Vision. In this module, we will consider volumetric representations for computer vision and 3D deep learning and understand how they are connected to the other 3D modalities that we have been considering previously, and also how we can construct volumetric 3D shape from range images. We will further look into how various data structures can accelerate processing basically of volumetric data. To this end, we will look into sparse, tensors, and octrees, and we will further consider dense and octree-based convolutional neural networks that operate on volumetric data. Let us start with revisiting the volumetric representation of 3D shapes and how it is related to different other 3D modalities. Next, we will look into how the volumetric representation can be constructed from sensor data in the form of range images. Let's start with defining what the volumetric representation of 3D shape looks like. Volumetric representations have basically the main advantage of being able to perform inside-outside tests quickly, it's basically conceptually the most simple and the most similar to color 2D images or range images that are defined by sampling a function on a regular grid. It also allows for fast data modifications with new information, such as editing. And it's also trivially converted from different sources of 3D data, as you will see further, such as LiDAR point clouds or RGB point clouds or CAD meshes. In terms of the geometry processing pipeline, volumetric data acts as the data source for downstream tasks such as reconstruction and understanding, where you can extract meshes or perform volumetric learning using volumetric grids. There is a number of ways how we can represent volumetric 3D functions. One of the ways it would be to store just an occupancy map, which is a binary function that maps each 3D location to a binary value, and the meaning of the binary value is to indicate whether the particular 3D point is inside or outside of the 3D shape. Then a signed distance function is basically defines a distance or an area of signed distance values, mapping a particular volume to a real line. Note that the distance function is well signed, meaning that it attains positive values outside the shape, that is, on the free space, and negative values inside the shape, in the areas where the space is occupied by the volume of the shape. Also, typically in applications, you will encounter truncated SDF or TSDF, that is the SDF where the max value is set to a fixed value sigma. So it's clearly related to the SDF by a simple formula. The voxel grid represents free space with positive values and occupied space with negative values. However, it is also customary to represent the distance using an absolute value as well. Let us see how this looks like. So on this figure, occupancy maps, signed distance function, and truncated signed distance function are compared visually. On the left, you can see the occupancy map, which is a binary map, meaning that all of the pixels or voxels are set to either 0 or 1. In the middle, there is a signed distance function, which is depicted by level sets of different color. Red color indicates that we're inside the shape, and blue color indicates we're outside the shape. And the truncated SDF resembles the SDF untruncated SDF, but basically provides also a threshold. You can see how the SDF-based representations kind of provide more information about the shape of the object, in this case a butterfly. In practice, however, we can be satisfied by truncated SDF, which sort of only stores distance values in the direct vicinity of the surface. Interestingly, functions such as TSDF can also be defined for single view depth images. So you don't have to have the full 3D shape in order to define an TSDF or SDF. For instance, in this figure you can see how the wrench surface on the left can generate an SDF function depicted in the pseudocolor on the right, because each point in the depth image corresponds to a depth measurement, which serves as a definition of the SDF itself. So a depth map is also a discretized SDF. So this makes SDF TSDF machinery easily applicable to large environments, such as entire rooms or areas, not just single shapes. So far we have only defined the actual function that we would like to somehow represent. However, this function is possible to represent using a variety of computational representations, meaning the data structures, which means how do we actually compute the value of the function. Sometimes it is possible to represent a function using a combination of basis functions, where you have a number of, well, basically basis functions b sub I, and you sort of evaluate each of the function and add them up with coefficients c sub I in each of the 3D points x. However, typically in practice, and we will look into that today and further in the tutorial part, you will be representing volumetric modalities such as occupancy map or SDFs using a dense volumetric grid, which is basically a 3D tensor of voxels or volumetric pixels that are basically axis-aligned cubes. And so evaluating f of x basically performs a table lookup. So you have the set of indices, and then you basically query your volumetric grid for a triple of indexes I, j, k. And sometimes you want to construct an implicit surface, and then you typically evaluate it using bilinear or trilinear interpolation of the values at the grid vertices. Other representations, such as hierarchical grid and sparse grid, store function values either at progressively finer levels by subdividing space using a specific data structure, such as the octree, or store only important cells or blocks of volumetric data, such as the occupied cells of an occupancy map or non-truncated cells of TSDF. Of these representations, of course, the simplest is the dense volumetric grid, which needs a cubic number of voxels where n is the spatial resolution. It is very much similar to raster images in photography. So in each cell you can store a binary occupancy mask or a signed or unsigned, possibly truncated distance value. Then the resolution plays an important role, since to represent a 3D shape at spatial resolution n, one needs to have at least n cubed voxels. So this once again means that memory requirements, for example, grow cubically with resolution, so does the compute. Right now we have not figured out, except for the dense volumetric grid, how to actually specify the representation, but how it is relevant to other available 3D modalities such as meshes or range images or point clouds. It turns out it's directly connected to all of these representations, specifically volumetric 3D representations, can be built from any of the modalities out there, for example, from point sets or meshes or CAD models, or you name it, through a very simple process such as voxelization. It can also be built from surface modalities, where you can obtain SDF or DSDF or occupancy map using distance to surface queries from the surrounding volume. And it can also be built from a number of sensed range images into a global surface model by fusing these range images through the so-called depth fusion process. You can also obtain occupancy grid or SDF or DSDF. Also, the volumetric representation is used in implicit surface modeling, as we will talk more about that in the next lecture, and also in the mesh extraction process that, of course, uses the implicit model of the surface. To voxelize a triangle mesh or a CAD model, we basically intersect each triangle with the voxel grid. So basically, all the voxels that are intersected by a triangle are set to 1, while others are set to 0. The same thing is valid when we would like to voxelize a point cloud. So point clouds are sparse, therefore the voxel grid that we are going to be obtaining as a result of this voxelization is going to also have a lot of empty cells. But to build an occupancy map out of a point cloud, we basically occupy a voxel if at least one point in the point cloud is within the voxel. This, however, brings us only surface geometry, as we're not able to see inside the shape, because meshes, point clouds, and CAD models typically represent only the surface geometry of the object, but not its interior. So in this case, the occupancy map is kind of unfilled, right? So we cannot have interior occupancy. However, in some instances, for example, when we're measuring volumes of objects, it is more convenient to obtain a filled model of the shape, with occupancy set to 1 inside the shape, but not only at the surface. To this end, we can use the so-called space carving approach, which is essentially a shape from silhouette. So such approaches, they operate on a discrete space, for example, a voxel cube. In this case, in the slide, we're only seeing the 2D projection of that. So it's basically an image grid, 2D grid, and we kind of have the camera pauses, and what we do is in each of the images that we take with the camera, we find the silhouette of the object, and then we kind of discard voxels that are projecting outside the silhouette. In the images in this slide, voxels inside the silhouette viewed by the camera 1 are depicted in pink, and the ones that are in the silhouette of camera 2 are depicted in green color. So by intersecting all of the voxels that project to, by discarding all the voxels that project outside one of the camera, we are able to obtain an approximation to the volume of the object. Right. So these techniques, as you can see, are quite robust and easy to implement. I also encourage you to watch the video on space carving from the computer file channel, which is quite popular. It's quite easy to understand, and it's also very enlightening. So in this case, we demonstrate the usage of space carving for first rendering depth maps from a geometry, and then using those depth maps to carve a dense voxel grid. So the result is a filled voxel grid of the given shape. So space carving is actually really useful for sequential attacks. For example, if you're given a sequence of depth images and your goal is to kind of determine where the filled volume of the 3D shape actually is, or for example, if you are given the current reconstruction and a list of previous camera poses, and your goal is to determine the next best view that kind of reduces the uncertainty in the voxel grid as much as possible. So in this case, your goal will be to obtain the depth maps either by using ray casting or the real depth map from sensors, and by voxelizing the entire space with a number of occupancy labels such as free and occupied, but also unknown is very important as well. And your goal would be to determine the next camera pose that would yield you the best reduction in the number of unknown voxels when we perform ray casting. So that's the next best view problem in this case. A way of also generating a volumetric representation from surface modalities, for example, such as CAD models or meshes, would be to use the familiar raycasting method, where one creates an array of 3D vectors that represent rays, and we basically create one ray per each voxel in the grid, and these rays are drawn according to the chosen projection model, and you basically compute ray surface intersection using the raycasting technique, and this gives you a distance to surface representation from a particular view in space. Let us further study how one can obtain volumetric 3D shape representation using a series of depth images, also known as depth fusion. So, when constructing occupancy grids or volumetric TSDF using techniques such as voxelization or space carving, it's kind of trivial to do. All you need to do is you kind of compute a binary mask and so on. But volumetric depth fusion is typically more challenging, and we're going to review it. So the input here represents a sequence of range images, D1, D2, and so on, optionally with known camera poses, meaning that they're kind of registered. In real applications, such as building a model of your room, however, you do not really have the access to ground truth information about camera poses, so you kind of have to somehow infer the camera pose given the current model of the scene and your current sensed image. And the goal would be to build a full 3D model in the form of TSDF function defined on a volumetric grid representation. So you can see in this slide there is an animation that actually shows the process of real-time depth fusion from RGBD camera, where you can see how the model actually updates incrementally as more depth frames are being used to build the reconstruction. And so this has been a popular technique in computer vision where RGBD cameras such as Kinect or RealSense that are able to actually deliver high resolution and high frequency depth at high frame rate have been used to actually build reconstructions of entire rooms. So for example, in this case, there is a room built using a technique called bundle fusion from a series of RGBD scans. So you can see there are walls and there are chairs and there's the floor, there are tables and scoffs. So you can build entire large-scale, high-resolution, dense 3D models of large scenes using such methods. Basically, the vanilla depth fusion method is from 1996 by Curlis and Levoy, which starts with range surfaces that are proxy surfaces obtained from range images, and builds a volume around the range surface. The intuition behind the method is that if we're given a range surface, which is essentially basically a mesh, then we can compute a TSDF, that is the distance from each of the subvolumes in the volume of interest to that particular range surface. And so when we obtain another measurement of the same surface, for simplicity, that is due to the acquisition noise or reconstruction noise, it is not going to be in the exact same spot as the previously sensed surface. We will be able to somehow update or average or fuse the newly obtained depth image into the already existing volumetric grid. So Curlis and Rivoy have developed a conceptually simple but very efficient method to actually perform depth fusion by rolling averaging each spatial location on the grid. Specifically, the formula for the volumetric depth fusion is presented here on the slide, where you can see how the resulting D capital, which is the value of the TSDF function in every location in the volumetric grid, is basically just a weighted average of the previously built TSDF volume and the newly sensed depth map. In this case, we also need to define what is called the weight functions that basically say how we should fuse the newly arriving volume into the volumetric grid that we're building. There is a number of caveats in defining the weight function. However, the conceptual method is very simple. Let us just see an example of the vanilla Curlis and Livoy volumetric depth fusion. We're starting with a single camera pose, and on the right you can see the actual current reconstruction from a single depth view that the camera pose is giving you, and also the cross section of the dinosaur here. So as we are obtaining more and more views, we will be gradually reducing uncertainty in the depth map. In this case, only a few depth views are sufficient to actually build the entire model of the dinosaur, and you can see also the cross section becomes pretty accurate over time. The method is actually simple and fast, and it also allows easy implementations. However, it has a number of disadvantages because many views are typically required to build a good reconstruction. While it is still possible with modern cameras that take depth at 30 FPS, it's still kind of suboptimal because you need to really have a lot of views to obtain the full reconstruction. And also, it cannot it doesn't have an explicit mechanism to actually handle outliers or severe noise. So basically it tries to fuse the noise into the model, which is also suboptimal, and it also doesn't have the surface completion. And because of that, many of these scans remain noisy and have a number of holes inside. So one method to tackle such a problem, for example, specifically it is very efficient in dealing with noise, is what's called the TVL1 depth fusion. It is obtained by minimizing a surface shrinking function. Also, basically, you're trying to get the same mesh or the same surface. However, what you are also trying to achieve is the minimal surface of the shape that you're obtaining by minimizing surface shrinking functional that takes into account the area of the surface and the proximity of the surface to the sensed depth maps. It integrates the prior on surface area and is able to efficiently perform noise reduction. However, it also leads to over-smoothing of the surface and sometimes to removing geometric features such as the sharp geometric features. Right. And it also cannot complete missing surfaces, of course, because it doesn't know anything about them. So volumetric 3D data are really generic regular representations for 3D. They are basically represented a number of ways, such as occupancy grids or sign distance functions that are encoded typically on a volumetric grid. Native implementation, however, will suffer from cubic dependence on the required resolution, but however, volumetric representations can be efficiently constructed with simple procedures such as depth fusions for a lot of other types of 3D data, and even simpler procedures if you would like to obtain just a voxelized 3D shape from a mesh. So efficiently describing scenes and manipulating 3D shapes using volumetric representation in fact poses a number of challenges in terms of actually storing the respective voxel data, because it scales cubically with the number of required detail. So let us understand how we can design a compact data structures that represent volumetric data for such tasks. The first data structure that we will consider is the vanilla dense volumetric 3D degrees data that are dense 3D tensors and matrices. And so recall the naive representation, the actual value of the distance function or the occupancy map is actually stored in each single voxel of the volumetric grid, and you will instantly notice how we must store voxels where there exists no data. Effectively, what we are doing, we are wasting memory and compute, and using TSDF instead of SDF volume makes little sense to employ high-resolution volumetric grids, as increasingly more space will be wasted, right? So actually, truly dense volumetric data is actually rare and only encountered in areas such as medical applications, for example, where you can have computed tomography or magnetic resonance imaging scans at high resolution that actually represent a meaningful piece of data in each voxel of the volumetric grid. But these are not the case for 3D scanning applications, for example, right? For where we only kind of care about the surface of the object and only sometimes care about the actual volume of the object that we cannot see anyway. Right, so increasingly more space is going to be wasted in this case. So to get an idea about how much space is actually wasted, let us consider the following simple observation, right? So on the left you have just the point cloud. As you know, the point cloud is defined by storing 3n coordinates of the points, basically. Optionally with RGB and normals, but fundamentally there's only the 3 coordinates of the points that are x, y, z, right? So assume that we're also given a mesh and would like to compute an occupancy map representing the entire 3D shape of a mesh, and we will voxelize the shape and just display it at different resolutions at progressively finer resolutions in the grid. We just start with 16 by 16 by 16 grid, which has an occupancy of only 4% already in the grid. But as we progress, we see, as we go from 32 to 64 to 128 to 200 and finally to 512 occupancy cubed, we'll see that we're losing efficiency. So at high resolutions, such as 512 cubed, the shape is actually very well represented. However, the amount of memory spent in the dense volumetric grid has also significantly increased, and also the waste and the efficiency of storing the actual data has been significantly degraded. So only a fraction of a percentage of the volume has been actively occupied. So this raises a question about how one can actually reduce the memory footprint required to store large amounts of volumetric data at high resolutions. So there are a number of answers to that question. And one of the answers would be to actually go for a sparse data representation. And this is important because sparse data representations have been achieving state-of-the-art results in learning recently. Sparse tensors are one way to approach a problem of storing arbitrary indexable data, in fact. So, in fact, this is applicable to more than just machine learning and finds use in many other fields such as chemometrics, for example, or physical simulations. So, many naturally occurring tensors are considered sparse, and they contain mostly zero values. And as with sparse matrices, various techniques can be employed to more efficiently store and compute on the sparse tensors. Right? So, let us actually review what we know so far. So for general volumetric datasets, storage requirements scale as n cubed, where n is the resolution along one spatial dimension. So for truly volumetric data such as MRI scans or CT scans, we really need to store all of that data. However, other datasets such as point-based sampling of surfaces leave much of the 3D space unoccupied. For instance, representing voxelized surface would only require n squared voxels, with nearly all values in the 3D grid set to 0 or some other inactive value, right? And also with the point clouds, like the image on the right is actually a voxelization, like a coarse voxelization of the airborne lighter point cloud. Only requires endpoints storage. However, what we are doing is we are storing the entire volume of the street in this case. So this all raises a question of whether we can design a more efficient data structure where only values in meaningful locations are stored while others are basically discarded. And so the answer to this question is a sparse tensor format, which allows to operate on unoccupied spatial locations of samples only. However, there are a number of sparse tensor formats, and so let us just look into what are the different formats and which format is reasonable to choose. Right. So basically, the sparse volumetric grid, what it does, it stores the occupancy map or the TSDF by k voxels, where k is the number of non-empty voxels, right? So the picture that you're now getting is you only store the actual active voxels instead of the entire dense volumetric grid. And because we only have submanifolds embedded in a three-dimensional space, like the surfaces, for example, or a set of points, we will end up saving a great deal of compute by doing this. So what are the possible sparse data representations? So let us just look at the number of them. The first up is just using a normal array, right? So if we're having a 6x4 matrix with a large number of zeros inside it, so the matrix is actually effectively sparse, right? So what we can do, just a no-brainer, is we store every value, even the zeros, and we do that consecutively in memory in a fixed order. And in this case, because the matrix is 6x4, so it has 24 values. So if we're taking a floating point data type, then we have to store 24 floating point values. And these are stored for example, in this case, in the row major order consecutively in memory. So this is called a dense array to disambiguate it from other sparse methods, right? So obviously dense arrays don't make any use of our assumption that most values are 0, so they can use lots of memory, but they sometimes are still the best choice because they're kind of the closest match to how modern hardware operates. Anyway, let's start with this simple, most common format is called a coordinate list, or COO. So for our matrix, we will store one entry for each non-zero values, and that entry includes row index, column index, and the value itself. So you can obviously notice that the actual efficiency of this format is highly dependent on the number of zeros in the value. For instance, in this case, since we are only having 24 values in the matrix, but only 8 non-zero values, what we end up with is we end up having exactly no benefit in storing the COO format instead of the actual row dense array format, because we still have to store 8 values of row indexes, column indexes, and the actual values. So we end up having another 24 values. However, if the number of elements in the matrix is actually high and most of them are 0, then of course we will have more benefits in storing only the active row and column values. A slightly more sophisticated format that exists is called compressed sparse row. So CSR uses, in fact, 3 separate arrays: values, column indices, and row index pointer. To fill them, we first get the COO entries for the sparse matrix, sorted by row, then column. So values is filled non-zero values in order. So in this case, the values will actually represent the values as we encounter them by traversing the matrix in row major order, left to right, top to bottom. So column indices are filled the column index for each non-zero value. So in this case, we have the column 0, 1, then 1 again, then 1, then 2, then 3, 3, 4, 5. Then the final array has size row count plus 1. In this case, we have 4 rows, and this means that we are having 5 values in the row index pointer. So each entry in this final value represents a row in the original matrix and indicates the first value in the value array that belongs to the row. To read values from a given row back out again, we first read a pair of values from the row index pointer array, and then use those to slice the other 2 arrays. For example, to read the third row, we'd find row index pointer 2 to be 4, and then row index pointer 3 to be 7, which tells us that there are 3 values in that row, with columns 4, column indexes 4th, 5th, and 6th, and values 4, 5, and 6. In other words, compared with the COO format, it avoids repeating the row index over and over again. As the values are ordered, we know that all values in a given row will be consecutive. We can say that the row data has been compressed. The column and value data is still uncompressed though, so it takes up as much space as it did in the COO format. The third one that is commonly used is something called the compressed sparse fiber, or CSF. So to obtain this kind of a format, what we do is we use compression on the first dimension and then group each of the values by their first dimension index. So in this case, we're having the first dimension is represented by a violet column in the coordinate format here. So we compress the first dimension by basically joining all the 1s together and all the 2s together to obtain the 2 nodes in the compressed sparse fiber format. So each value in that group is identified by its remaining n-1 indices. In this case, we have 3 indices left. In other words, it is itself an n-1 dimensional tensor. right? So in this 4D example, we split it on the first dimension to give 2 fibers. Now we have n-1 dimension tensors, and we can talk about how to store them. So the natural approach would be to basically repeat the process. This will give us basically like more sub-tensors and more fibers. So we compress a dimension, you group into sub-tensors, and you repeat. If the data is already sorted correctly, you don't even need group, just find where the runs start and end. So the result is a tree-like data structure. The values are not shown, just the indices. And so actually the division here basically displays how the first split is being performed by splitting along the first discontinuity in the first row into 2 subtensors 1 and 2. Another way of actually accelerating processing of volumetric data would be to use a special data structure that is not sparse. So many of you know that binary trees and binary search trees provide a convenient way of actually representing sorted data, and octrees are actually also sorted trees that are designed for efficient spatial indexing of three-dimensional space by recursively subdividing it into octants. So it's often used in 3D graphics and 3D game engines. It provides an attractive way of computing raycasted images and solving many other tasks. In this case, many applications such as 3D spatial indexing or nearest neighbor and location queries or visualization and raycasting, they do require an efficient tree-based data structure that is able to actually represent geometry at sufficiently high resolutions. And it's directly related to volumetric 3D representations that are the focus of this video. So an octree is a search tree, that is, it represents some sorted data with exactly 8 children in each node. So what you do with an octree is you recursively subdivide space into 8 octants at each spatial scale. So you go from the entire volume, you divide it into 8 parts, and then the parts that you need, you divide again into 8 parts, and so on and forth. So in the matrix-based octree, the subdivision point is implicitly the center of the space that the node represents. So you kind of split it in half along each dimension. And the root of the matrix-based octree, it actually represents a finite bounded space, so the implicit centers are well defined. In this animation here, you can see that each of the blocks here, the flying blocks, actually reside in one of the leaf nodes in the octree, where you can solve collision detection, which determines for each pair of the flying blocks whether they are in the same innermost node of the octree, and that kind of indicates the potential collision. So nearest neighbor search in an octree takes only a logarithm of the number of voxel in each dimension, and also insertion, which kind of maintains the octree that you get to perform if you add more data. It also takes a logarithm, so this makes it a very efficient data structure for indexing basically spatial data. So our butterfly example gets represented efficiently by an octree which is a reasonable computational container for the SDF function, where it is able to store only the active sites, that is, locations with high variation in the signal, and it also bypasses the need to load multiple identical values in the grid, because all of them are represented in the parent nodes of the tree, not the innermost nodes. In fact, what we're showing here is a quad tree, not an octree. So octrees and quad trees are 3D and 2D brothers. As you have seen in animation, the octree data structure can efficiently represent the real value distance function or the occupancy grid, and also where the latter is changing or requires increasingly high resolution. So to wrap up the spatial data structures, we have seen a number of various data structures. So the simplest one is the off-the-shelf dense volumetric grid, which is just a 3D tensor consistent of voxels. It's easy to use, however, it is very memory and computationally inefficient. In fact, in many applications, it's basically prohibitively inefficient. You cannot use it at high resolutions, and also you will gonna waste a lot of compute in using it. And then the hierarchical grid, or quad tree / octree, stores function values at progressively finer levels, increasing detail where more variation in the signal is required. So it is fast in terms of insertion and search. However, you gotta have to maintain a separate data structure, and it's still pointwise constant approximation to the signal. So it's an axis aligned octree. And the sparse grid, or a hash grid, only stores important cells or blocks of volumetric data, which removes redundancy for storing or computing values in empty voxels, but you also have to maintain a separate data structure and implement all the necessary matrix multiplication or tensor multiplication operations, including on the GPU, for example, using the COO formatted sparse tensors. However, nowadays, a number of libraries such as CUDA sparse library provides implementations for sparse tensors, so this is not a very big issue anymore. Now that we're familiar with the most basic blocks, we're ready to see how neural networks can be defined to operate on 3D voxels. We will start by describing a naive approach to construct 3D convolutional neural networks, and then extend it to a more computationally efficient octree-based networks, which is another variant of volumetric models. We will skip the sparse variants for this video. Let us first review the conventional 3D ConvNets and see how dense 3D CNNs can be utilized. So when the input is a 3D volumetric grid of values, such as, for example, 3D occupancy grid or a volumetric GSDF, it is very tempting to basically directly extend the notion of 2D convolution to the third dimension. This has been successfully done previously by numerous works. And so 2D convolutions are actually a mainstream tool for processing signals. So everybody uses CNNs to process images and videos, and RGBD, for example. So by just adding the third spatial dimension, it is very basically attractive to basically directly extend 2D convolution to third dimension, which boils down to basically adding another loop into the code for convolutional computation, right? And this has been done previously. So much of the 3D CNNs are busy basically in understanding 3D scans. So, for example, semantic segmentation, where what you have is a bunch of images that are basically used to reconstruct a scene. So, for example, in this case is a scene of an apartment that is represented by occupancy map or Also, it could be represented using a mesh. And the goal would be to construct neural networks that provide understanding of what is where and what classes, objects, and voxels have in this kind of environments or scenes. And you can sort of see in the reconstruction of the apartment how various objects differ from one another. So, for example, you can see how the bed differs from the chairs and tables, and there are also walls and so on and forth. The goal here would be to generate the full geometry and understand objects in a scan. Of course, the two general mostly used representations in 3D deep learning are occupancy grids, the binary ones, and also the implicit function that is also defined on the voxel grid. So, for example, the TSDF will be an attractive option here, and a lot of networks just use that. So they define a 3D convolution in the way that is depicted in the slide. So, for example, in this case, this is CVPR 217, and this is the ScanNet paper that basically defines a 3D convolutional neural network that classifies each crop or segments each crop in a 3D scene by passing it through a bunch of 3D convolutional layers, which process occupancy values and possibly RGB values projected onto the voxels. So these are dense 3D CNNs that operate directly on the voxel grid, and these values are these networks are very similar to the vanilla 2D convolutional neural networks, such as, for example, AlexNet, the older ones from the early days of deep learning, of the modern deep learning at least. So to give you an example of what these models are actually able to achieve, here are the voxel predictions, the per voxel predictions of the networks, and here is the ground truth. And you can see how the networks is actually able to approximate the semantic segmentation label for these apartment scenes very accurately. In fact, there are multiple scenes represented in the slide. So these are all volumetric reconstructions. They're literally built of little voxels here, even the visualization of these. So these has been the understanding tasks. But one obstacle that kind of stops from obtaining more efficient reconstructions and more efficient understanding for 3D scans is that the 3D reconstructions are actually very noisy. For instance, in this reconstruction, you can see that the overall quality of the resulting room reconstruction is high. However, there are a number of issues with the reconstruction. Specifically, you can have a lot of holes in the reconstruction. So this incomplete scan geometry issue has been very impactful on the quality of 3D understanding. So typically why this is happening is because you're physically unable to scan in certain parts of the scene. For example, certain parts of the scene contain cavities or other obstacles that prevent from scanning in specific spots. Therefore, you have occlusions. Also, some of the sensors have physical limitations. For example, their range is insufficient to scan in certain parts of the scene. But for example, for applications such as games or VR, we cannot have models where a lot of arbitrary holes are present in the model. So this means we gotta complete these scans somehow. So therefore, we are arriving at a task where from a noisy scan, we need to actually obtain a more complete scan of the same scene or object. And so 3D shape completion tasks have been extensively studied in literature on deep learning and 3D deep learning, including by our group at Skoltech and by many others, for example, by the group of Matthias Niesner from Technical University of Munich, whose results we will shortly see. And so actually the way it works is we construct a 3D CNN that accepts a distance field and packed into a 32 cubed voxel grid, and it actually predicts a more complete 3D representation, 3D TSDF value by passing it through a 3D shape classification and further an encoder-decoder network. And the result is the completed shape. By adding another database prior, the result can be further refined by a multi-resolution 3D shape synthesis architecture that kind of keeps you like more detail in the shape by also increasing the resolution in the underlying voxel grid. But to focus on the 3D CNN part, the actual 3D encoder-decoder network is actually a dense 3D convolutional neural network that accepts a 3D volume of 32 by 32 by 32 TSDF values and convolves it using a series of 3D convolutions to obtain a hidden dimension, and then decompresses it using deconvolutional layers in 3D to also the same volume with distance field predictions. So such models also typically, as you might or might not know, they include skip connections that kind of connect the layers on the encoder and decoder part, the branches in the network, by passing data from the encoder to the decoder part, which also helps in training and in copying the data over to the actual decoder branch. So this model is possible to train on real world or synthetic data, but it also helps to recover, is able to recover the global structure and keep you a good amount of detail. So for example, given an input that is depicted in the upper row in the image, you're able to complete it to the middle row. And if we compare that to the bottom row, we can see that the actual completions are pretty accurate, even though they're not perfect, which is reasonable. And given that the network has been trained on the synthetic shapes, then it is very impressive how the network is able to actually recover the global structure and keep a good amount of detail, and also keep you like sharp curves where they need to be, right? So these are really the results that you are able to obtain on like separate shapes, but this is kind of boring because what we would like to really work on is this, and these are the reconstructions and volumetric scenes at large spatial extent, right? So you, in fact, when you're like working with the real data, you really never know what the actual real spatial extent of the scene that you will be inferring on will be like. So for example, in this case, this is an entire floor of a building that consists of multiple rooms and so on. And so the question would be, what about the entire scenes and domain transfer, right? So because we are training on separate parts of the scene at during training time, how can we actually execute the inference during test time? And the answer is that we are able to do this using fully convolutional nature of the 3D convolutional neural network. So it's actually very attractive and nice that the actual convolutional neural network is able to obtain the inference in a single shot on this entire scene. And the way this is performed is we're typically training on blocks such as the one on the left here. So for example, these are the many blocks that are fed into the network during training. Of course, you can have various augmentations such as rotations and various voxelizations, but in the end what you do is you're basically training on fixed size blocks such as, for example, 64 cube or 32 cube, and you test on the same completed blocks. And however, on the test since you're able to actually perform completion at basically any resolution, because the network is fully convolutional, so you can actually test it on arbitrary spatial extent. And the way it works is actually remarkably good. So for example, in this scene you can see how the test input data actually looks like. It is severely corrupted by under complete geometry, and the network is actually able to predict everything very well. You can see the chairs, and for example, you can see the chair and the structural elements are present in this meeting room.
Method that takes an incomplete 3D scan of a scene of arbitrary spatial size and predicts a complete 3D model along with per-voxel semantic labels. Method that takes an incomplete 3D scan of a scene of arbitrary spatial size and predicts a complete 3D model along with per-voxel semantic labels.
Complete project by Matthias Nisner and colleagues, and it takes as input a partial scan of the scene and predicts
we take as input a partial scan encoded as a sign distance function. Method that takes an incomplete 3D scan of a scene of arbitrary spatial size and predicts a complete 3D model along with per-voxel semantic labels.
One question would be, however, do these two tasks, or like predicting completed geometry and also simultaneously predicting semantics, do they actually help each other?
So the question is,
surprisingly, that semantics, it doesn't really help to predict geometry. However, learning a good geometry completion model massively helps to predict semantics. So this is one takeaway from this work. Of course, the downside of the 3D convolutional neural networks done naively would be that the actual memory requirement and compute is really does scale cubically as the resolution increases. For example, to infer at 128 resolution, you would be required to already have 20 gigabytes of GPU memory, which is prohibitive in most situations. So most current GPUs only have like 16 gigabytes of memory. And this is due to the nature of 3D convolution. So we cannot escape the curse of dimensionality in this case. So just to wrap up, the naive 3D CNNs or the dense 3D CNNs, they directly extend 3D convolutions to third dimension, which is of course suboptimal as it is so computationally inefficient because it scales cubically with spatial resolution. So this forces you to actually use either low resolution shapes or crops of real scenes such as 32 cube or 64 cube, or use shallower neural networks. And this is really bad for deep learning, because much of the deep learning has been leveraging the depth of the models that we're using. So many applications, though, can still leverage low resolution volumes, for example, the semantic segmentation or scan completion applications that we have seen previously. However, we have seen that some of the 3D convolutional neural networks are actually also sample inefficient, meaning that they are not able to achieve the accuracy that the sparsified or, for example, octree models are able to attain. So let us switch to the octree models. Let us finally consider the octree-based CNNs that are based on the prior indexing of 3D data into a spatial data structure known as the octree that we have previously considered. So using efficient space partitioning, it is possible to achieve efficient feature learning on the octree nodes. So our goal would be to actually train deep architectures at high spatial resolution. So most existing 3D network architectures, they replace this 2D pixel array by the 3D analog, so they use a dense and regular 3D voxel grid. So if you process this grid using 3D convolution and pooling, as you have seen, computational memory requirements, they grow cubically with the resolution. However, what we need is a high resolution inputs and also high resolution outputs where necessary, and therefore we need to fully exploit the rich and detailed geometry of the 3D world. And the reason why would be contained in this example. So for example, these two pairs of examples, they depict different classes of objects. However, if you voxelize these objects at significantly coarse resolutions, such as, for example, 8 cube in this case, you can see how the instances of the objects are remarkably close. However, as we increase resolution all the way through to 64 cube, you will see how the objects are actually different. For example, the bathtub is different from the bed. But however, to see this, we need higher resolution inputs. So in octree nets, the spatial data structure is used inside the network, which has cells potentially spanning multiple voxels, with larger cells far away from the surface and finer cells that cover areas near the surface. More specifically, a grid of shallow octrees is used. A shallow octree is an octree of fixed depth, so it covers a fixed number of voxels. If we place several of these octrees in a grid structure, we can cover the whole volume quite efficiently. Regarding network operations, it is necessary to define the network operation specifically for this data structure. Let us describe the convolution. For the convolution, you would apply the filter of weights the same way as you would do it in a uniform grid. But the results are different responses within the same octree cell. However, we would like to keep the memory footprint the same, and therefore we would like to summarize the responses. We can do that by pooling, and this forms the result of the convolution operation. So as you can see, the convolution for octree nets is defined in a custom way with custom tensor operations that need to be implemented in the CPU and GPU variants efficiently, which represents a significant technical challenge. However, in the end, the result of all of these operations is differentiable, therefore we can do end-to-end training in this structure. Another operation that needs to be defined is pooling. However, the previously defined convolution yields results that are already pooled. Therefore, the pooling operation is only relevant for the smaller octree cells indicated by the red color. We pool them, but then we have to decrease the resolution of the octree. The way it is implemented in the octnets is by combining neighboring shallow octrees. So we can repeat these operations once again on the same resolution and combine on neighboring shallow octrees. To evaluate the octree networks, what we can do is we can increase the input resolution for the network by several times and see how the model performs in terms of the memory efficiency on the GPU. So, for example, the dense network only feeds in a single GPU if we limit the input resolution down to the 64 cube. However, the octree network can easily be fit on a single GPU with 4 times the same spatial resolution. Also, the runtime scales favorably for the octree networks. In terms of the accuracy on, for example, ModelNet 10 and ModelNet 40, what we can see is that the dense and the octree-based models are actually indistinguishable in terms of accuracy. Specifically, the networks perform basically the same on the ModelNet tasks for a number of resolutions in the input. However, what is important for the ModelNet dataset is that you only need like the resolution on the order of 16 cubed to be able to actually capture most of the geometric variability in the dataset. In this case, this is a classification task. So other tasks such as, for example, rotation estimation are needed to actually characterize the performance of the octree net at higher resolutions. So octree-based convolutional neural networks, they define a convolutional and Boolean operators on top of octree data structure. And they possess a unique capability to train deeper architectures at higher spatial resolutions.